As we know, the ancient Greeks were well known for their use of geometric constructions to prove mathematical facts.
To the Greeks, number was synonymous with length. All of their numbers represented a constructible length. In other words, a length that they could construct with a compass and straight edge. They thought that the number line contained only rational numbers because those are the numbers that they could construct. And between any two rational numbers, since there's infinitely many more, it was a logical conclusion that only rational numbers were on the number line.
They felt that all numbers could be represented geometrically on a number line. Let's, by construction, locate the natural number 5 on a line. To perform this construction, we'll need a working line. On a smartboard, which is what I'm using to produce this video, it is very easy to produce these lines, so I will not be using a straight edge. It is also very easy to produce perpendicular lines. For example, if I draw another line here, I can snap it to what I call perfect verticalness, since this is at perfect horizontalness, if you'll pardon my expression. So what I've done is I have located a place to start my line. And now what I'm going to do is I'm going to mark off 5 equal segments along this line, starting from this working point here, through the use of a compass. So I'll bring my compass up here. Here it is, beautiful compass. And what I will do is set a particular length on my compass to be my unit length 1 and not change that length. And what I will do is I will strike arcs along this particular line to make the location readily seeable, which will be 5. Okay, I've done 1. Now I'm going to 2. Three, 4, and finally 5. So if I clone this particular segment, first of all, let me get the compass out of the way. If I clone this particular segment here, or line here, which I can easily do with the Smart Tools, I can drag it over here, put it right on top of that location, and you can see that this location would be called the natural number 5. Next, let's construct a segment of length 8/3, or equivalently, find the exact point on the number line with coordinate 8/3 or 2 2/3. This construction will involve using a number line which has already been pre-marked. Now you realize for this number line we could have used a compass to mark off each of these equal segments, but we'll assume we have done that already. To help us out with this instruction, we're going to need a number line which is perpendicular to this one. So I'm not going to do this by construction, but I'm instead going to clone this particular number line, and then what I'm going to do is I'm going to take its clone and place it in a perpendicular position to our number line that's already here. I can do this by snapping it to perfect verticalness, knowing that the bottom number line is already in a location of perfect horizontalness. So now I will take these and place them, and I'll put it here, so that these two are exactly perpendicular to each other. What I'm going to tackle first is the construction of the distance 2/3. What I'm going to do is construct a right triangle on these two number lines. This right triangle will join from this point here 3 units on the vertical number line to the first point on the horizontal number line. Now what I'm going to do is this. You will recall there is a theorem of mathematics which states that parallel line segments which are equidistant from each other will divide a transversal cutting the parallel lines into segments which are congruent or identical in length. As you can see here then, AB, BC, and CD along this transversal would all have to be identical lengths. Keeping this theorem in mind and having blown the figure up to a little larger size to make it easier for you to see, I'm going to now construct parallel lines to this particular side of the right triangle, the hypotenuse, through the points shown here, this one and this one. To do that, I would generally have to, by construction, create those parallel lines. But I can do that on the smartboard by simply cloning the lines and moving them. Now remember, if you were doing this construction, this would be a lot more complicated. So what I'm going to do is I'm going to take this segment, I'm going to clone it, and you can see that it is perfectly parallel to the segment that is here already. What I'm going to do is slide it down so that it goes right through the point 2 units above on the vertical axis. Notice I can do the same thing again. So if I clone this segment and I move it and place it through the point which is 1 unit vertically above the horizontal number line, what have I actually done? What I've done is, because these 3 segments here have to be the same length on this transversal, this transversal has to have 3 units of exactly the same length as well. It's an extension of the theorem we already talked about. Therefore, this segment from 0 to 1 has been divided into thirds. So if I take 2 of them, this length must be 2/3. Also note that since the 3 segments drawn across these number lines are parallel, the right triangles they form are all similar. This means since on the larger triangle's longer leg exist 3 congruent segments, its bottom horizontal leg must be in proportional thirds as well. So by adding in the numbers on the number line, and by taking the compass and using it to determine the length 2/3 that we can strike off after the number 2, we should be able to complete our construction of the number 2 2/3. So it appears we have the correct length marked with the compass. So I simply go over here and strike off the arc, which gives us the correct length for 2 2/3. Our ancient Greek mathematician forefathers began to run into trouble when having discovered that not all numbers can be expressed as the quotient of 2 integers, or as rational numbers. This became apparent when Pythagoras noted that a right triangle which has sides of 1, or legs of 1, exhibits a hypotenuse which had a length that is irrational, that being radical 2. This brings us to another question. Can I construct the square root of 2 on a number line? Well, let's take a look. I'm going to build this construction from scratch. That is, I'm going to start with a working line and then construct a number line on this working line. I will locate my first point, the value 1, at an arbitrary distance along the working line, and then place 2 more points on my number line. So I will bring up my compass, and I will choose on my compass an arbitrary length to use to strike my first arc. So placing the compass on this point, getting it there as closely as I can to where it should be, I will strike this arc, but I'm going to strike this first arc in a little different manner than one would expect. You'll see shortly why I've done this. And what I will do is rotate my compass, bring her back down, put it on the point which I established as 1, and I will now strike my second arc, and moving the compass over, I will strike the third arc, so now I have the points 0, 1, 2, and 3 on my number line. Still attempting to demonstrate properly the construction I have begun, I must extend the number line I've created a little more than 1 unit to the left. So I have extended, using the Smart Tools, our number line more than 1 unit to the left. Next, I wish to construct a perpendicular line through the point 0 on the number line. Therefore, I need to extend my arc of unit 1 so that it will intersect our extended number line. I will now construct the perpendicular bisector of the segment between 1 and what would be -1 through the point 0. To complete the perpendicular bisector, I join the 2 points formed where the 2 arcs intersect, and I now have my perpendicular line segment through point 0. Why, you might ask, did I do all of that? Well, I wanted to produce a line segment of length radical 2. I'm going to remove the arc work lines here, used to construct the perpendicular bisector, so as to simplify this figure. You can see that the perpendicular bisector has a point on it, 1 unit above 0. I will now join that point with a segment connecting it to the point 1 on the number line. As you can see, the right triangle now formed has legs of 1 and a hypotenuse then of radical 2. So to complete our construction, all we need do is use our compass to copy the segment of length radical 2 onto our number line. We have thus constructed the irrational number radical 2. A crisis resulted for the ancient Greek mathematicians caused by their discovery of irrational numbers. It was later discovered that not all irrational numbers are constructible. A perfect example of this is transcendental numbers. A transcendental number is a real or complex number that is not algebraic. That is, it is not a root of a non-zero polynomial equation with rational coefficients. These topics are beyond the scope of this course. However, the best known examples of transcendental numbers are pi and e. You know, we've heard a great deal about a special number called the golden ratio recently. I wonder if it's constructible.